Welcome to the lecture on Introduction to Physical Modeling. So, in this lecture we are going to talk about the principles of modeling, in what different way the modeling is to be carried out for the tundish steel making process. So, if we talk about the modeling term, as we know that modeling is a well established scientific technique with widespread application in engineering process analysis, design, control and optimization. So, as we know modeling is a very much known term nowadays. Most of the process is being modeled, and we use different scientific techniques, and its use is in the different areas. So, it is used for ascertaining the characteristics of the system. Many a times we do the modeling first, and then we try to have the plan for further execution of the processes. So, in the case of modeling, now normally when we talk about model, so in the case of steel making, you have either the physical model or the mathematical model. So, physical model will be something in which we make a physical setup, and in mathematical model we are making a model which will be set of equations or expressions, and it will be talking about the behavior of the system, and that is used for the prediction of the parameters and its effect on the flow characteristics or other related processes. So, it implies scientific representation either physical or mathematical of a process or a phenomenon. In physical modeling, a given phenomena is investigated in a replica of the actual industrial unit, while in mathematical modeling given phenomena is investigated by mathematical expressions. So, as we discussed that normally whatever we try to model, many a times we make this small model of that particular experimental setup or of any process, and there certainly there are many kind of changes, because there is another term that is pilot scale experiments. So, there also you do the experiment, and there again you have the scaling done. So, in the case of physical model, basically when we talk about the steel making process, so in the case of physical modeling, not necessarily, and in fact not at all. I mean, we normally use the different working fluid, because it is very difficult to work with experimentally on the working fluid as molten steel itself. So, what we do is we take the different kind of working fluid. Normally we take water as the working fluid, and if we talk about the material of the tundish or the ladle, so that material is also not the actual one which is normally a refractory lined vessel or so. So, here we use the perspex sheet as the tundish or the ladle. So, that is your physical model, and if you talk of the mathematical model, so mathematical modeling will be carried out by representation with the different set of equations. These equations will be the governing equations, and they will be talking about the processes, conservation of either mass, momentum or chemical species. So, this way you have different set of equations, and this involves the knowledge of mathematics or science and engineering to have those expressions which truly represent the processes which are occurring. So, that is your mathematical model. So, in that case you have mathematical expressions which are used for the modeling. So, if you talk about the need of the model, if you look at the model, so you have the physical model, and then you have the mathematical model. And in physical model you have normally scale up or you can scale down. So, normally you go for a scale down. So, you can go for the scale up or scale down. Then in physical model you can have the cold model as well as the so if you try to have the classification of the model. So, if suppose you have basically you have one is a prototype. So, prototype is the actual size. Now, in that you may have you will make a model. So, from here you will make a model, and that model may be by scaling up or by scaling down. So, you can go by scaling up or you can go by scaling down. So, that way a model is made. Now, that model, so this model further will be one is physical model and another is mathematical model. So, we will be talking about the physical model in this lecture and this week. And we will talk about mathematical modeling part further as we move forward in this course. Now, in physical model you can go for the cold model studies, and otherwise you can also go for the high temperature model. So, so that way you can go for the so cold model means the working fluid will be at a room temperature. Because it is very difficult many a times to work with the working fluid which is actual, that its temperature is more than 1500 degrees centigrade. Now, in that there has been working fluids which are being used, and either you can use water as the working fluid, or even many a times some people have worked and taken the mercury also as the working fluid. So, so that way your physical modeling is carried out, and mostly we do go for the cold model. If you go to high temperature model, so they are also done with some different kinds of metal, and in that basically you may have the use of metallic melt, or what we talked earlier, that you have pilot scale experimentation which go on. So, they are part of this. Then if you come to mathematical, so in mathematical model certainly you are making different type of equations. These are conservation equations, and then we apply the boundary conditions which are subjected to the domain, and accordingly we try to predict the output parameters which are of interest to us. So, that is how this you can have the idea about the development of model, either physical or mathematical. So, coming to physical modeling with a physical model to represent the system in majority of cases by changing the scale or size. So, in fact you have a physical model which is in front of you, and you work with it, and that is used for representation of the system. In most of the cases we are changing the scale or size. So, normally we are reducing in most of the cases. So, if suppose in industry you have a tundish of say 2 meters of or 3 meters of length. So, you can have a reduced scale model, physical model of 1 meter length. So, that is because the handling of the larger vessel that will be problematic. So, we make the smaller models, but certainly accordingly you will have to change many things that we will discuss later. In steel making, so we are normally we are using physical models with perspex sheet, and water is used to represent the molten steel. So, normally the models are made with the perspex sheet which is transparent, and that is strong also. So, you can have the the tundish made by the perspex sheet, and that can be fabricated by the fabrication techniques using glues and so. And since they are opaque, transparent, so you can see from outside also and study the flow behavior which is going on inside the perspex tundish. Then we use water to represent the molten steel, and there are reasons for that. One is that water, if you talk about the kinematic viscosity of water at room temperature and that of the steel at its own melting temperature, they are somewhat similar, they are very much closer. So, when we talk about those similarities, in that case when we talk about the fluid flow and other analysis, so in those cases we can go with that. So, that is why water is mostly used, and also water is easily available. So, and in water also this is being transparent. So, when we do the tracer dispersion studies, you can have the visualization in a more transparent, you can see it, properly visualize it. So, that is why water is used. So, objective is to measure and visualize characteristics of the real system. So, studies of high temperature steel making provide useful insight into the system, which is impossible otherwise, because you cannot have the visualization on the actual system where the steel is flowing. So, because of the very high temperature, and also it is not transparent. So, what is happening when any kind of diffusion is taking place, or any kind of alloying elements go into it, or there are inclusions, how they are going to float. So, or in which zone the steel is still showing stagnation or so. So, these things can be seen by visualizing the flow behavior when you have a color contrast when we put the tracer inside, and by that we can have an insight of that using the physical model. So, that is why physical modeling becomes very important when we talk about the tundish steel making. It is used to validate also a valid mathematical model. Many a times this physical modeling is used for the validation purpose, because as we discussed that either you will have to go for the actual plant readings, or you will have to go for the pilot scale experimentations. Then only you can have the actual data and you can have a a prediction about the behavior of the system. So, many a times what we do is we work on the physical model, and from there we are getting certain results, and from there we try to validate it. So, if we are getting accordingly the similar kind of results for the actual cases also for certain parameter, in that case we say that the model is validated, and then further the predictions of many kind can be made by using these mathematical models. So, that is the beauty of the or usefulness of the physical model. Physical modeling and mathematical modeling are frequently applied in conjunction. So, many a times when we are going for mathematical modeling, we do the physical modeling, so that there is more of the faith in the scientific manner can be put in onto the mathematical model. And when we do the physical modeling, so there can be infinite number of experimentation, permutation and combinations. So, maybe we can do it using the mathematical model, and then accordingly we can limit those set of experimentations to have the prediction, to have the prediction of these input parameters on the output performance measures. So, most of the time when we go for physical modeling, we also do the mathematical modeling, or if we have to go for mathematical modeling, we also make the physical models. If we talk about the mathematical modeling, so as we know it is A mathematical model is a set of equations, algebraic or differential, to represent and predict certain phenomena. So, that is how the mathematical models are made, and these equations are the equations which are governed by certain principles. Just like if you go for the flow in the tundish, so it will be governed. So, since the molten steel is a fluid and it is flowing inside, so for that you will have certain conservation equations. So, they are used. So, you will have continuity equation, or you may have the momentum conservation equation or so. Reliability of the mathematical model largely depends on how rigorously the model has been made. So, how rigorous the model is, or how rigorously you have made the model, because many a times when we are making the model, if we try to replicate the true conditions, so many a times these conditions are very complex, and it may be also very difficult and many a times impossible also to take the complete whole set of actual conditions. So, there are many compromises also made, there are some assumptions made, and accordingly the model is made. So, but if you to the larger extent you make to take the account of, you are taking the account of these realistic conditions, the more rigorous the model is and more reliable it will be. So, so that is about the reliability of that model. You can have the use of modeling in steel making involving which will be involving complex processes which are like multi-phase turbulent flow, heat and mass transfer, chemical reaction. So, these are the different domains where the modeling is being carried out, like you have the modeling of the turbulent flow. So, flow of the liquid in the tundish is turbulent. So, there you will have to have those turbulence quantities taken into account. You will have to have different type of turbulence models taking into account, which should be predicting close to the values of actual like velocities or turbulence quantities or pressure or so. Like similarly the heat and mass transfer, because heat is being transferred towards the wall and towards the surroundings. Similarly, there is mass transfer diffusion taking place, or chemical reactions are also taking place. Then relatedly you have the different domains inside the tundish and all that. So, all these are the areas where the mathematical modeling is being used. Numerous idealizations are applied to formulate reasonably realistic process models in steel making. So, that is what we discussed, that you will have to have many kind of you will have to make certain adjustments, you will have to take the assumptions and all that, and then you get some process models in a realistic manner. So, many kind of idealizations are applied, and nowadays the mathematical modeling is a very good tool. It is very much popular. It is because of the efficient solution algorithms, and also you have very good computational solvers. So, because of these things nowadays we have the freedom to go for the mathematical modeling. We do it in a very small time. We try to reach to the actual results. So, basically that is because when we talk about mathematical models, in that case there will be errors. These errors will be depending upon certain kind of assumptions we take, or certain round of errors will be there because of the truncations which we do in or the truncation errors are there in those governing equations. So, based on that there will be certainly certain errors. So, so many a times we make the grids very smaller, so that takes more computational time. So, because of the evolution of very good solvers as well as very good machines, computers which are extremely fast nowadays, we are in a position to do good modeling studies of the real systems. Mathematical modeling will be offering many advantages like low cost. So, if you are comparing with a system of the actual experimentation, then these cost on those mathematical modeling where you need one computation system and then there may be certain programming softwares or programming tools. So, they are actually very small as compared to what we do actual in actual cases, the experiments with actual system. So, you will have very low cost, good speed. In normal case, if you want to do the experiments, it will take large amount of time to set up the experiment and then getting the results properly, it will take large amount of time. Whereas, in the mathematical modeling you can do it very quickly. I mean as compared to that, then you can have the simulation also of real conditions. You can give all the you can get most of the information whatever you feel from the mathematical model by changing your programs. You can have the informations about the output parameters. So, that way these are the advantages of the mathematical modeling. We talked about another kind of trials or models which are made. So, that is pilot scale trials. So, as we discussed that many a times you have to use the similar fluid. So, in the case of physical model, we do not use the same fluid. So, we are making a physical setup, normally scaled down models, and we do with water. However, we do the real scale experimentation. So, but then I mean real scale experimentation is not done, but we do on a smaller scale. So, that is known as pilot scale. So, they will be normally smaller, but then the working fluid or the material of the equipments or so, they will be actual, like they will be normally 5 to 15% of the full scale system, but then the actual tundish will also be a refractory lined vessel. Similarly, ladle will also be a refractory lined vessel or so. So, you will have the material which is used will be the same as those in the full scale system, but it is smaller. So, the handling is somewhat easier, the cost involved is somewhat less as compared to the actual system on which we have to get the details. Pilot scale systems are inexpensive to build and operate. So, basically as their sizes are smaller, so you will have to invest less amount of money or less amount of resources for building these pilot scales, and you can have the feel of the actual system running. So, you will be looking at the those you can be looking into those aspects also which you are not able to see in the physical model using suppose water as the working fluid. So, suppose about the heat transfer, you can have the actual data in the pilot scale experimentations. However, you cannot get it for the physical models. If we talk about the physical modeling in the tundish, so as we discussed that we are using water as the working fluid for the realistic representation of tundish melt flow. So, when we use this water, so we can use it for studying the various aspects of the melt flow. So, these various aspects are namely like you have a liquid splashing from the plunging jet during early stages of tundish filling. So, you will have the plunging jet and then it will be coming and then there will be liquid splashing. So, that can be studied. effect of open stream pouring on air or gas entrainment, slag emulsification and entrainment, and their effects on fluid flow pattern. So, this is another area on which you can have the physical model preparation. Similarly, on the free surface of the tundish you can have the wave formation. So, these can be studied, and even there is surface turbulence. So, they can be seen using the physical models. You may have the flow visualization in different areas of the tundish. So, in the different areas, whether you have the different like you have different volumes, like can be computed by the proper flow visualization, whether the domain is active or not, the tracer which has gone, which is going to the certain section or not. So, that can be seen using the flow visualization, and also we have nowadays tools by which you can even see the velocity vectors in at different planes or so. Velocity and turbulence measurements in the liquid using probe. So, as the flow inside the liquid is normally turbulent, I mean inside the tundish is normally turbulent. So, you can even measure these velocity and turbulence quantities in the tundish or in any vessel using the proper probes, like you have laser Doppler velocimeter, so or you have hot filament anemometer. So, these are basically the turbulence measuring instruments, so that can be used. You can do the RTD study of the fluid. So, RTD is the resonance time distribution study. So, basically that we do by the tracer dispersion studies, and by that you can have the feel of the time for which the individual fluid particle is trying to stay, or on an average what will be the stay time of the fluid inside the tundish. So, that is your residence time distribution. So, you can have that at different points inside the tundish. Simulation of inclusion, transport and flotation. So, that also can be done using the physical models. You can make a model and you can have the inclusions of different shapes and sizes of different material which can float inside the liquid. So, accordingly you will have to have the density of that inclusion also been taken, how they are transported to different regions of the regimes of the tundish, and how they are floating up. So, these can also be predicted. Vortex formation and tundish slag entrainment during draining of the melt from tundish. So, many a times when we are draining the liquid metal from the tundish to the mold. So, there may be vortex formation, as we had discussed earlier. So, when it will reach below certain level, then the vortexing may occur. So, and in that case there may be slag which may go from the tundish towards the mold, or for that matter from any vessel, if it goes into the next vessel. So, that also can be physically modeled. So, you can have a slag kind of layer at the top of the water, and then you can do the experiment and you will see the emergence of this vortex as the level goes below certain critical value, critical height. So, these all things basically can be modeled using the physical models. So, physical modeling that way is very efficient, and efficiently you can do with the proper experimentation, and you can further predict. So, when we make the physical models, at that time you will have to have certain considerations to be kept in mind, and these are about the similarity issues. So, you will have the 4 different states of similarity. I mean normally what we try to maintain, and they are basically defined as the you have the geometric similarity, you have the kinematic similarity, you have the dynamic similarity, you have the thermal similarity. So, basically they should be similar. I mean if you talk about the geometric parameter, geometric similarity, so the ratio of these geometric dimensions of the model and the actual. So, they should be same. So, there should be a constant value. Similarly, when we talk about the static or you have the dynamic similarity where the forces are taken into account, thermal similarity where the heat transfer ratios at any point between the in the model as well as in the actual system. So, all these so we will discuss it about it in our coming lectures, that these are the different similarities which we need to keep in mind while talking about the making the physical models. So, this should be satisfied, then only we can ensure that there is proper physical model is there, and the prediction which is made by the physical model, it will be representing the in actual the the process parameters or output parameters which will be taking place in the industries. So, that will help the steel makers to decide about the choose of proper process parameters. So, about this we are going to have the discussion in our coming lectures. Thank you very much.